So hello everyone, and happy to restart this session after coming back.
Hello sir.
Hi, nice to see you again.
How was your vacation?
Oh, very nice. So it's almost time. We have one more person. Not sure if so. As before, I've been a while. So, do you still plan to simulate the motor?
Actually, I thought that I will first complete the course that I have taken. So I have just completed today or maybe yesterday. Yesterday I completed. So I will start working on that. Meanwhile, I have a different idea or a plan in my mind. So we should discuss it today.
Sure. So yeah, hello Eric. Just a quick, nice to meet you. I believe he's on mobile.
Just give me a sec. So sorry.
No, I'm not sure if anyone else will join, but about this is for Eric. I mean, you are joining from a mobile, but I have heard that mobile connectivity, or at least using this on mobile, is not very stable. So if possible, if you could use a laptop, it would be much better. Well, okay. So I would say that if he's willing to just listen, that's fine. Otherwise, we can continue.
So I will share my screen.
Yeah, sure.
So can you see the screen, sir?
Yeah.
So this is a battery model, lithium-ion cell. Actually, these are the equations of terminal voltage, and this is the equation of state of charge. It is a basic means it is not very basic means very easy battery model. Not useful actually, but just to start learning how to model the cell, I decided to go with this. So basically, this is a terminal voltage, which is a function of open circuit voltage, which is a function of SOC, and this is means drop across the internal resistance, and this is the Coulomb counting way of finding out the SOC.
Basically, it's a large capacitor. That is what you've used. That's the idea. Yeah.
Yeah. So and this is showing just two different resistances while we charge the cell, the resistance is different, and when we discharge the cell, the resistance is different according to theory. So this is the approximate diagram. This I have drawn a block diagram how it would look in a Simulink model. Okay, so we are giving a constant current command here. It will integrate and it will be divided by the entire capacity of the cell, and what we get out of it will be the SOC at that instance of time. Okay, and these two are the lookup tables. Okay, so it will give us the open circuit voltage for the specific SOC which will be integrated, which will be the outcome of this integration. Okay, and this is the resistance of the internal resistance of the cell corresponding to the state of charge, and this is the equation of that terminal voltage. So this open circuit voltage, when we subtract with the drop across the internal resistance, we get the terminal voltage. So this is what it would look like in a Simulink model.
Okay, so the first equation, I'm not sure if it's right. Can you go back to the previous slide? So you see that the state of charge is equal to the state of charge initially minus the integral of the current divided by the capacitor, right? So the initial charge is important. So now if you go back to the next slide and you see that equation, you see the first one, you are integrating the current directly to achieve the state of charge. So basically what is happening is, it is like this, like if assuming that the battery is supplying current, let's say that that direction is positive, if the current flows in that direction, the battery is discharging. So therefore, as the current is being supplied, charge is being depleted from the cell. That is how it is with respect to the initial charge. And if the current reverses, then it means the battery is charging, and in that case this integral will result in increase of charge. So you will have to add a positive a summation there and put the state of charge the initial state of charge.
So here you are saying that I should put a summer and give us take an input of initial charge.
Yeah, and also the current has to be negative, because the convention that we are using is that this current is a discharging current. So if we assume, let's say if we start with a battery that is completely uncharged, then any current that the battery draws will result in the charge gradually accumulating.
Yes.
So that's it. That's the only thing. Okay.
Yes. So my only concern here is how to implement lookup tables, because the other part of the circuit is fairly simple. We can implement means integrator and that all things are normal. But how to implement these lookup tables in Python Power Electronics or in a raw Python? So this is what I wanted to know from you.
So you mean when you say lookup table, it means how do you choose the resistance given if it is charging or discharging?
So I have a data set of that. See,
Okay.
this is the state of charge ranging from 0 to 1. Okay, it is incrementing by 1%.
Okay.
Okay, and this is the open circuit voltage corresponding to that SOC. This is the charging resistance and this is the discharging resistance. For instance, today we can consider only one thing for charging, but that I can extend further. So this is the data circuit for particular SOC. These are the open circuit voltages, and this is the internal resistance. So this we have to take, like in MATLAB we can import a Excel sheet. So somewhat similar, is it possible here also?
It is possible. You can use, I would say, if that is the case, the best way to do it is to sort of straight away go into data science and import this as an Excel, as a data frame.
Yeah.
So what we can do, what I would say is, in your control file, you should read this this Excel sheet, right? Create a data frame. And if you let me have a look at the Excel sheet again. So now if you look at, see the state of charge, open circuit voltage, resistance, and charge resistance, discharge resistance. Now to be able to use a lookup table, you need, okay, I'm just trying to see what it is. The current you will be measuring, because this is the current which is connected to the battery. So either you can say you are connecting to an external voltage source, putting a limiting resistance, and then measuring the current, or whatever method you are using.
Or we can put a constant current source as well.
Exactly. So then that is done. Now the next part is, we need the capacitance, right? The capacitance. So how do you calculate the capacitance? Is that a parameter, or do you plan?
No, it's not a capacitance. It is the capacity of the cell. Means, for example, 2.6 ampere hours or 2.3 ampere hours, whatever it may be. So it is a typical value of a lithium-ion cell of one capacity of the cell.
Okay.
So it can be given as a constant.
You mean the C, the value of C that you have shown in that thing?
Yes. Capacity of the cell, we can assume constant for normal operations.
Can you show me the equation again? Okay, now do you have any literature? Because from what I know, this capacitance is a kind of a model of the cell as a capacitor, a large capacitor.
Yeah.
That is
actually model of lithium-ion cell is very complicated topic, but this is very very introductory level how to model the cell. So this is not going to be useful anyway, but just to learn how to model a cell and how to implement if we have a data set, because whenever we model a cell, basically there is a test conducted in battery cyclers, and that test data we incorporate, we take that data and we build the cell model of the cell for computational purposes. So assuming that this is the data set what we are having, we are computing the SOC and we are measuring the resistance at each SOC, and we are noting down the open circuit voltage. This is a data set that we are having, and we want to develop a simple model that we run. If we run while giving a certain current, we will see in the output what is how the battery charges, how much time it takes, and how the charging graph looks like.
Okay, so what you're saying is for now we can just assume some value of capacitance. It does not be.
Yes.
So that's fine. We value. Okay, so now we assume a value of capacitance. Can you show me the Excel sheet now? So we have the current. With the current, we have the capacitance. We assume the capacitance, and with these two, we can now calculate the incremental charge, or as the charge as it is building up, right? Now, do you wish to map that to the first column, that is state of charge? Is that what you are trying to do?
Yeah, means basically here in the second slide, what we are, these two values, the value which comes out of this open circuit block and which comes out of this means the value of the summer block. So these are the open circuit voltages for the specific open circuit for the specific SOC. What is the SOC of the cell at this point, and this block will give us the internal resistance value for that particular SOC, and those values will be used for in that instance, in that integral loop, and we will get those value and we will subtract it, and we will get the terminal voltage for that instance, that sample time.
Okay, so I see what you're saying. So you want to calculate the SOC, and if you show me the Excel sheet, once you have the SOC, you want to interpolate exactly where you are, calculate the open circuit voltage, the charge resistance or the discharge resistance, whichever you are trying to do, and from there you want to calculate the rest of it. Okay.
Yes.
So hey Darius, we have restarted again. It's just the two of us. There was another third person who joined called Eric. He was trying to join on his mobile, and apparently he had some connectivity problems. I don't know if you want to try to contact him.
Okay, yeah, I can do that.
Yeah.
I think getting the rhythm back. Did you guys? So curious, Mikhail, did you receive an automatic reminder for the course today?
Yeah, just 10 minutes before I got the mail that this one's going to schedule.
Okay, cool. Okay. All right, yeah, I'll follow up, but yeah, well, I presume that as you get back into the swing, things should build up again. But
yeah, no, I think he was trying to join on his mobile, which I believe is not very good, at least with this API.
Yeah.
So
okay.
I don't know. He seemed like in some kind of a parking lot, so I don't really know. Would not also help in reception, so.
Yeah.
All right.
Okay. All right. Carry on. I'll follow up on this stuff. Thanks.
Okay, cool. Okay, cool. So, Nikhil, you can continue sharing. We can keep working.
Yeah.
Okay. So, what our problem definition would be as follows. For example, what I would suggest is this. let us say, okay, can you show me the Excel sheet again once? And do we have a state of charge? So it goes all the way to 100% state of charge?
It goes up to 1.
Okay, so 1. So
we have 101 samples ranging from 0 to 1.
Okay, so they have not made complete. Okay, so see, the trick here is we need to map between the capacity which is given, and we need to create that into a per unit value, because what has happened is, can you show the full open circuit voltage at 100% in the Excel sheet? If you look, yeah, if you go all the way down, no, if you just scroll down, that's okay. It's a 4.3 volt, 4.3 volts. It's probably 4.5 volt or something like that.
No, it is generally 4.2.
4.2.
Upper voltage is 4.2.
I see. So that means now the challenge here is we have the capacity of the cell as ampere hour. We have the state of charge in percentage or per unit, because it's from 0 to 1. We have the voltage as a full proper number, that is 0 to 4.2, right? And of course you have the resistance, which is charge resistance, discharge resistance, as ohms, again full value. So now the biggest challenge here is in creating this model is in mapping the value of C to a full proper charge. So now what we have to do is we need to calculate the actual charge for a particular value of C with that particular value of current, right? That's what you have to do. So first and foremost, what I would say is, we have, let's say for example, the rated current, right? Let's say for example, the rated current of the battery.
So generally if the capacity is say 3.2, so in that case the 1C, according to 1C rate which is recommended for charging, it is 3.2 amperes. 3.2. So if we charge using 3.2 amperes, the full the cell will be charged in 1 hour time.
Okay, so now using this, let us try to calculate how much will be our actual charge, right? So for example, let's say we are charging this at 3.2 amperes for 1 hour, which means 3.2 amperes for 3600 seconds. Alright? So how much would that be?
No, that we have to initialize first what is the capacity of the cell, that we can assume whatever it may be. So typical value may be ranging from means it can be up to 2 to 3 amperes. Ampere hours. Okay, so what I have used, that was 2.6 ampere hours. Okay, so for that, if we charge using 2.6 amperes, the entire cell will be charged in the time of 1 hour. So in this case, we have to initialize what is the C, capacity of the cell, and if we charge from 2.6 amperes, then it should be charging in 1 hour.
No, the thing is like this. Let's say for example, you want to create a model of this cell, right? Now, when you create a model of this cell, let's say as the cell, let's say we assume that the cell is fully charged and we are discharging, okay? As the cell is supplying current to, let's say, a load, as the current is being drawn, right, the charge will fall. Now, the problem is this: if you assume a particular current, right, and let's say keep that current constant, right? Actually, it won't be constant, because as the cell is supplying, the voltage will drop. But let us suppose, for instance, that the current is constant. If this current is constant, as time goes, the charge will fall, right? Now, the problem is this: how will you know where your charge is in that Excel sheet?
No, according to this, if we integrate the current, then it will give us the charge.
Exactly. So that's what I'm trying to say. Yeah. So we need to be able to do that, so that we are able to interpolate, because that's the main thing here, to be able to interpolate so that you can use this model.
So what my understanding goes is, if we whatever is the current, okay, if we integrate that current in each sample, in each loop, whatever current, whatever charge we are producing, that we will add in the existing amount of charge. Okay, that will be integrated in each cycle, and the whatever will be the accumulated charge, if we divide it by the total capacity, whatever we are left is with is will be the percentage of SOC of the cell. So if you can see this thing, so this thing will give us the SOC for that that time, accumulated SOC of whatever the time instance we are there. Okay, so then this SOC we will be comparing with this lookup table, and we will extracting the open circuit voltage, and we will be using that particular open circuit voltage here for this calculation.
Okay. Okay, so I guess what we'll do, you want to start writing code, then we can figure out what to do.
Yeah.
Okay. So basically what we can do is we can start a new simulation. You can just call it, let's say, battery model or whatever you want. So,
yeah, and also this time duration, what we are initializing first, can we give it a variable name so that we can declare it in the script?
No, this has to be constant. This you have to actually give a proper value only.
Okay, so here we can by default can give 3600.
Yeah, you can do. Yeah.
Okay. That's sample size because it is a long simulation, so sample size is should we increase the step or?
Yeah, you can make it 1 millisecond. So yeah, you have to create a new file. Don't put a space. Huh? Usually, because sometimes when you put a space, the operating system, you have to sometimes put a quote or you have to put a slash, so it becomes a little bit different. Operating systems handle it differently.
Yeah, even the slash direction is also different in Linux and Windows.
Yes. Yeah. So you can now start with the circuit file. Yeah, you can add a circuit file. You can go over to a spreadsheet. So what I would say is, let us take, since it's a 4.2 volt battery, let us choose a 5 volt DC voltage source. Connect the 5 volt DC voltage source to this cell through a resistance, let's say 10 amperes, 10 ohms, sorry, not 10 amperes, 10 ohms. So what will happen is, we have now our source voltage connected to our battery, which is a controllable voltage source. Through a resistor, we measure the current and we measure the voltage across the battery.
voltage source. Here Rn, and further we are
just pull that all the way, and basically first create a series path, put our controllable voltage source.
Controllable voltage source in parallel of this.
Yeah. So basically controllable voltage source will be the battery, and then
Okay.
across that we will have this voltmeter. It's a controlled voltage source.
Control voltage source. What we can give?
Cell battery, yeah.
Okay.
And you just connect. You can connect a voltmeter across. Yeah. And I would say we need at least 1 ammeter. So it can be anywhere, because voltmeter will not draw much current. So it can be either in the cell or it can be in the source.
Here only.
Yeah. Now there's only one thing. If you look at the control voltage source branch, it has zero resistance. So I would say put some negligible resistance there, because otherwise the simulator will not be able to solve. Okay, good. Okay, only one thing I would say is, for the sake of making sure nothing happens, delete the empty 3 lines above and the 2 lines below. So just try to put your circuit in this. I don't think it matters, but just to take into account that I've not used Windows much. In Windows it might, the Excel sheet, because a CSV file is saved as a text file. So as text file, sometimes if it sees empty lines above, it may just move everything up.
Okay.
So just in case. Okay, so now you have to just save it as a CSV file. Just make sure it is in the same directory, that's all. And also make sure the CSV file save type as. Best is CSV MS-DOS. If you look at CSV MS-DOS, that is the best, CSV MS-DOS, because that is like plain text. Below there is CSV Macintosh, CSV MS-DOS. Just keep going.
Yeah, CSV MS-DOS.
That is usually the best and the safest.
Yeah, definitely.
All right.
We'll add this circuit.
Okay, good. Yeah, you just have to click process circuit schematic.
Okay, no detectable error.
Okay, let's keep going. So, go to edit circuit parameters. So, yeah, the current direction. Now here, if you want the current direction to be the same as your model, I would say reverse this. Because now, if the current is entering the cell, then it is charging the cell, right? Whereas the positive direction of current with respect to the cell is when the current leaves the cell. If you look at your PPT slide. So I would say just reverse the ammeter direction.
1A we have to say.
Yep.
Control voltage source.
Now, control voltage source is, all I would say is you just have to give a control name to it, which is a little unique. So for example, you can just call it the name. So you can call it the cell. So like for example, you can give it the same name as the component. Or you can think of something else, whatever you want. Only thing is, this is actually not so important. This is mainly for debugging purposes. But the idea is later I would like to create some kind of debugger through which you can kind of debug your control signals. But this right now is no use. It's like, doesn't really matter. But still, I would say start building it, because if I release a new version, you can do something with it. Okay. The positive polarity is upwards, which is fine. So you can leave it as it is. Initial voltage, if you want, you can put something or you can remove. I don't know.
According to the cell sheet, initial voltage means it starts from 2.4. It can't go below 2.4.
Okay, so you can give it 2.4. No, you went to -5. You put the initial voltage is -5. Yeah, okay. Now, resistor, you can just, this is the cell, now this is the cell resistor. This has to be negligible. Because this is actually, it is best to have it negligible, because even the charging and discharging resistor that we are trying to do, it is better that we put it in through code.
Let's keep it very small.
Okay.
In initial resistance, so that we are giving 5 volts.
Yeah. So you take it this way. So 5 volts and 2.4 volts is the lowest possible voltage. So that means 2.6 volts. Now with 2.6 volts, you want to restrict your current to 3.2 amperes. So
whatever may be the ratings, whatever we will decide the rating of the cell, by that much current we want to allow.
Yeah.
So considering 2.5, we will put 2 ohms of resistance.
Okay, that's fine.
Registered and voltage source, keep it 5 ohms.
You have to remove the AC parts. The peak voltage, frequency will all become 0, because this is an AC, by default an AC voltage.
Okay.
And positive voltage is also up, positive polarity. So okay, good. So So I think the last is the voltmeter. Yeah, it can remain 120 volts. Only thing about the voltage level is make sure it is much higher than the system voltage. Since we are only 5 volts, this can remain as it is. Now, there's one thing which I missed. If you look, we have taken the voltage of the cell into account, right? Because the control voltage source. But we also want to model the charging resistance or the discharging resistance, right? So we have taken a constant resistance as R cell. Okay. So actually speaking, that is a mistake. We should actually replace R cell with a variable resistor. So what I would say, go back to your circuit and instead of resistor, make it variable resistor. Because now what happens, you can set the value of this variable resistor from code. So now you have to go back to your simulator and go back to the add circuit page, and you have to process your circuit schematic again because you have made a topological change. Yeah, so you can go back now, edit this. No, actually edit circuit parameters. So here if you look, now you will see a variable resistor. So again the same thing, give it a control name which can be the same as a component name. So just call it R cell or whatever. Now the initial resistor value, we do not have to initially, we can just not give it much, we can continue to give it a small value, make it 0.1 or something, because what our main objective is in trying to calculate this and mapping it to the Excel sheet. Of course, that I don't think we can do that today, but we can do that next week. Continue, right? So if you save it, right? So now what happens? We have now completed our circuit. So you see what we have done? We have taken a control voltage source for now as the initial voltage of 2.4. It is connected to a DC voltage supply of 5 volts through a resistor of 2 volts, 2 ohms, right? Now, this circuit will work as it is without any control file. So what I would say, let's run this circuit and then let's add a control. So you can just...
Okay, but we have not created the list of this internal resistance.
That's okay. Let's at least run it and make sure that it is drawing a current.
Okay. Okay.
So like what I'm trying to say is that this is how whenever you build a simulation, you should build it bit by bit. So always go to the command line, check out. Yep, running. So now you can add the plot. So you can check out the current and the voltage. Mainly current. The voltage you know is going to be constant. Yeah, that is the one. Yeah, you can plot it. You can plot it. See what happens. So the reason why it's negative is because it's charging, which is expected.
Yes.
Most important is, you see, even with the lowest possible voltage, with 5 volts power supply, that is input power supply, we have a current of 1.2 amperes, right? Which means that even in the worst case, this will not be supplying, or at least it will not be drawing current that is more than the rated current.
Okay.
Right? So that's what it means. So now that this is done, we can stop the simulation. We can now start writing some control. So the first thing what I would say is, let us now integrate this current, right, and try to see what the charge looks like. So let's say, for example, we do 1 by C integral IDT. Okay, good. So as always, in this model, let us say first things what do? We are now creating a model, right? So we want to integrate, right? Whenever you are running a control file, it is always advisable that you create the first variable that you should create always is your time event, right? So go back to the simulator and let's start. We add this control file and configure it. So first one, time event variable. So you can now go to your control file. So always in the control file, you know what to do, right? Right. There is no semicolon in Python. Huh?
Oh, sorry. Okay. And we have to create the template.
No, first you have to create an if block always. That is, if t clock is greater than the time event, and greater than equal to always, usually. And always colon, because this is a conditional block. And then here at the end, give one space and then put increment your time event. Okay. So this is like a quick initial setup of any control file. Okay. So now that we have done this, the next thing we can do is we can set up our input, right? So the input first input that we are interested in is the current, right? So what you can do, go back to your simulator and you can go to your control input. Say you can add a control input. Yeah, give it any name. I would say copy that variable and put it in your So this is your current, which is cell current, which is available to you, right? Now this is the input current. What we need to do to integrate this, you know how it is, we have to create a static variable. So for static variable, you go back to your simulator and define a static variable.
Static variable we are creating for?
To integrate the current. Because we are going to be integrating the current to create what is the incremental state of charge that we are going to get, right? And then once we have that state of charge, basically what I want to do is I want to slowly start integrating and making sure that what is our limit. And then once we know that this is our limit, then we can convert that to a per unit form, because only if you convert that to a per unit form, then we can use the Excel sheet.
Okay.
So call it anything, current integral, whatever you want. It's an integral, basically it's an integral. So you know how to do, right? Integral means you have to put it like in the left hand side. So integral is equal to cell current into dt. You have to put a plus equal to, because you are integrating. So it starts at 0 and it continuously integrates as the current flows, right? So this is your integral. Now the next part we have to do is to be able to map this to an SOC variation, right? So whatever is this integral, this is the variation in the state of charge, right? So now we can define our capacitance. So on the head of the file, you can define what will be the value of C, or you can call it cell cap, whatever variable you want. Okay, so now okay, just 1 minute. There is a mistake in your indent. If you look at integral and look at T1, there is some problem. They are not on the same line. Okay, now they're okay, fine. So this integral, you have to divide it by cell cap to find out the difference in SOC, right? So I would say you can now create that variable.
So we have to create that SOC variable.
Yeah. So since it is a variable, it's always recommended to use a static variable, because it is something which can change continuously and needs to be memorized. You need memory.
SOC.
Okay, so now let's say, for example, actually this is SOC variation. This is not SOC because it's the SOC variation, but that's okay. Now, what will you do? Go back to your slide. So you see, you have to implement the second equation. SOC is equal to SOC 0 minus 1 by Cn integral IT dt. Now you have calculated this 1 by Cn integral IT dt, right? So now the next thing you have to determine is what will be your initial state of charge, right? Now in this particular simulation, if you want, you can start at 0. That's not a problem, right? So I would say create another variable called init SOC and you can initialize it to 0.
Or maybe we can keep this SOC for this particular purpose, and we will initialize different
that's also fine.
For that.
That's also fine. Actually, you don't need another static variable, come to think of it, because the integral, whatever is there, you just have to subtract it. So that is good enough. Yeah, you can just leave it. You can ignore it, that's okay. So if you see here, all you have to do is SOC minus equal to this integral divided by cell cap.
SOC is equal to
Okay, so it's important to understand that this is the variation SOC. SOC is equal to SOC minus this, right? So you have to put a minus equal to sign. Right. So now that we have done this much, what I would say is let us plot it. So create a variable storage element. Okay, so now you can copy that thing. It should be all the way below. And you can use it here and just say that plot SOC is equal to the SOC. Yeah. So now you can run this file and plot your SOC. Okay. Okay. So this is why I wanted to run it, because it is always the numbers, because see, you're always playing different type of numbers, right? So you see the problem here is we chose the capacitance as 2.5, right? So which means you have a 2.5 farad capacitance, right? It's like your battery has a capacitance of 2.5 farad. That is huge, right? So now the problem is, for example, it's like this. You see what's happening? Now the next thing you see is we've already plotted again. We've plotted for 70 seconds because these are in seconds, right? And you're plotting it for 3600 seconds. You can plot it again and we see the latest results. So you see, it's going, if you continue this way, it will go out of bounds. So the first thing we have to note is, one, we must cap our SOC, right? Because so what happens is we must cap our SOC at a certain value, because once the capacitance is, our battery is fully charged, SOC cannot increase any further. It is at 100%, right? So the first thing you must determine is what will be your max SOC. That is 1 per unit, but this is not per unit.
So 100.
Again,
or maybe the
value.
capacity. So,
exactly.
okay. So 2.5.
Okay. See, thing is like this. You have to, see, it's important to understand what it is that we are actually looking at. Now, 2.5 is the C value, right? That is the capacitance. Now, SOC is the state of charge. That is not the same as your capacitance. So again, like I said, the question, what is charge? Q is equal to C into V, right? Or you can say Q is equal to integral I dt. So if you assume that your battery is being charged by the maximum current, let's say 3 amperes, for whatever is the time period, the way it is defined. So let's say if it is 3 ampere hour or whatever, 3000 whatever ampere hour, if you supply that much amount of current for so much amount of time, then you will achieve a certain amount of charge in the battery. So now this will be your maximum charge. And you must limit it at that. So what I would say here in Python, you can specify that. See, if you go to the head of the file, you can put that value. So what is your max SOC? This you can call it max SOC. So go ahead and write it.
So we are using per unit or 100%?
Now it is 100% because what happens is here, in this Python code, you are dealing with all real numbers. See, this is the challenge which I said. The Excel sheet, one column is in per unit. All other columns are in full absolute values. So your greatest challenge in building a model is going to be is to map the per unit to the actual values. That is your main challenge. Once you can do that, then you can scale whatever value you are getting again as per unit, and you can load your Excel sheet and do the interpolation. Okay. So first thing, max SOC, what will it be? Let's say your cell capacity is 2.5, right? So 2.5 multiplied by 3600 is how much? How much? No, sorry, not 2.5. 3/3. It's something like, how much you said it was? What is the capacity of the cell?
2.5 ampere hours.
2.5 ampere hours. So if you say 2.5 multiplied by 3600, what do you get? That is your total Q. State of charge is basically your Q charge. So Q is equal to integral IDT, or Q is equal to current into time. So that is your max SOC. Yeah. So max SOC is cell cap multiplied by 3600. Right. So now what you have to do is, after calculating your SOC, you have to check if SOC is greater than max SOC. If yes, then you must cap it. That is, you say SOC is equal to max SOC.
So after this SOC, we have to put the conditional statement.
Yeah.
Okay. SOC is greater than or equal to max SOC, then we have to stop, means
you have to limit it. Yeah, it is a limit. So now what happens, you are saying if it is greater than or equal to max SOC, SOC is equal to max SOC. That is, it will not rise beyond the maximum charge.
Okay.
Alright.
From this point, it will not increase.
Yeah, because it is fully charged. It can't charge more than that.
Okay, but now we are playing just using commands, but we are not doing anything to the current input, because basically what we do current 0. We stop the charging. So instead of doing something like this in form of code, can we do something that our current gets 0?
That is the next step. So that's what I'm trying to say. Now, once you know what is your state of charge, now you must calibrate your state of charge as this is your 100%, right? So now that you have calibrated your state of charge, you can define what is your per unit SOC. Once you have per unit SOC, you can compare it with your Excel sheet, know where you are, calculate the voltage, and set that voltage as an output of this control file. So this control file will take the current as input, give output as voltage. That voltage will be fed to your controllable voltage source, which is now constant. So as the state of charge increases, the voltage of the controllable voltage source will increase until it becomes the same and the current will stop. But for the current to stop, you must decrease your input voltage to be the same as your max voltage of your cell. Right now it is 5 volts, which is greater than your max cell voltage. So you can reduce that to maybe 4.2 or 4 volts. So then what happens, when your cell charges up fully, it will not take any more current. Current will go to 0.
So in this if statement itself, in the next line, we initialize the voltage source to be equal to the cell voltage.
No. That's the thing. So now this is your task for the next week. What you have to do, first plot it. See what you're getting. At least try to analyze a little. The next thing what you have to do is, you have to say that this max SOC is 100% or 1 per unit. Now, at any given point of time, what is your SOC? As a percentage of your max SOC. Right? Now, this max SOC that you have, you must now map it with your Excel sheet. Now, you've already learned pandas and everything else. So, you can read that Excel file and use some Google. Again, you can probably will be in SciPy or NumPy.
Yeah, we can use dictionaries for that, right?
Exactly. So, that's the thing. So, basically, you must find out where the SOC lies, interpolate it between two values, and find out what will be the voltage corresponding to that SOC. And then when you find the voltage, that voltage will be your output of the control file.
Okay, so let's first simulate this and see what are the changes.
So now you see it is capping. So what is important is now your cell has completely charged and is remaining constant at the charge.
But one catch here, in approximately in 5 seconds, our capacitor is fully charging, but technically it is not possible. It should take 1 hour, a full 1 hour to reach its saturation.
Yeah, so that is what, now the next, which is what I wanted to say. So you see what is happening here. The main thing if you see here is that this capacitor, right, the value of the capacitor you have chosen to be 2.5. Right, now this 2.5 is ampere hour. That is not the same as farad.
Okay.
That is not the same as farad. So you cannot choose the C value that you have chosen the same as the ampere hour. That value is going to be very different. And that is how you must map it so that this state of charge becomes maximum in 1 hour. And that too, second thing you need to know is you must supply the maximum, a current close to the maximum current. Right? So play with your value of resistance so that the current goes up to, let's say, around 3 amperes. So that then you can adjust your C so that you can go up to around 8000 or so SOC in 1 hour. Okay. Anyway, so we've started this. Like I said, this will take our time. It's okay. We can continue next week. But I think you have enough tips to go ahead with this simulation for a while. Anyway, if you need help, you can always post on the Google groups.
And one more thing, just maybe we can discuss for 2 to 3 minutes. If we are simulating any DC-DC converter, okay, so whatever components that we are using, like for inductor, now I have done that course, so I know what is inside the inductor, but diode and switch, whatever we are using in that, whatever library that you have created, do we have the access to see how you are modeled it?
Yeah, it's all open source, right? You have to go into circuit, elements.py. If you go to circuit elements.py, all the components are defined there as classes.
Which folder?
No, you have to go into the source code of Python Power Electronics. You go into simulator interface. Inside simulator interface, there will be simulations folder.
Simulator, see this simulator, then this PP.
You can show your, you can just share your screen again so that I know what it is.
See this.
Yeah, so you go to simulations. So you see circuit elements.py.
Yes, okay.
So here you see this is a resistor class. So this way you go down, you will see all the models, all the elements have been defined here. So these are all Python classes.
Okay. So if I want to search for a particular element, like for switch, so how do I?
Just do Control F switch and you will come to that. Switch will be the last, I think. Yeah.
Okay, last switch. Okay. So okay. So no, why I'm asking is this because I was thinking to do something like whatever we are simulating. So we have if I want to see the what do we say, efficiency. So how much losses are incorporated in this particular topology? What is the input power that we given and what is the output power? So I want to do the analysis of the losses in the particular element. Like for in switches, what is the loss? Like for in diode, what is the loss? In all the inductor, what is the loss? So that I want to give it a theoretical quantization. Like this is the losses and these are the contribution of each and every element for that particular loss. So I wanted like for LT Spice and all those Spice softwares, they have the exact model number like for a MOSFET for a particular MOSFET, they have the specific model for that particular MOSFET, so that we can if we are working on any live project, we can use that model so in the simulation as well, so that we can compare the actual and simulation losses. Like I hope you are getting what
See, what in that case what you will have to do is you have to calculate an equivalent resistance for the switch. You have to place that in series, right? Then you can put a voltmeter across the switch, put an ammeter in series with the switch. You know the current, you know the voltage across.
But the characteristics are different for N channel and P channel.
No. In this simulator, those characteristics are not there. It is not, I don't model total, because then you have to put in a lot of other details. You have to have the capacitance, you have to have an inductance. There's a lot of other things. That is not there.
No, I just wanted to find out whether it can come very close to the actual physical circuit or not. That's why I wanted
You can. Like I said, it is all you have to do is come up with a circuit model. Like it is basically like, right? A switch has several capacitance. There is a capacitance, there is a resistance, there is a resistance between the drain and source, there is a capacitance between the drain and source. So if you model these, you will get more or less the same thing.
Okay. So is it possible that I model a switch and we can use that in PP?
You can try.
If I do that.
You can try. You can always try. I do not work in the device characteristics, so I generally do not go that much into it. But if you want to build one, you are always welcome.
Okay, thank you. Then I will see, because I was also doing some LT Spice simulations, and there are some if we search on internet, we get the realistic models of the particular component. Like for diode, whatever diode we are using in physical circuit, the model is there available by the manufacturer or someone who has done that. So I was curious whether we have used in this platform as well.
Like I said, I don't deal, but I don't see why it should not be possible. It's just that I do not work there. The reason is, like I said, the main reason for me to simulate is I want to simulate large circuits. Even these LT Spice models, if you go detail, you cannot simulate large circuits. They will start hanging. For example, if you take 5 converters, 10 converters, and you put every switch model, diode model, it will hang. Almost no simulator can handle that much, unless you go into something like hardware in the loop and things like that, or you start using FPGA. It is not possible to deal with that amount of calculations. It is too much. So, which is why I don't deal with it, because my main interest is microgrids, renewable systems, like large systems. So I don't deal with device characteristics, but I don't see why it should not be possible.
No, and a very basic question, is it really required? Because like in simulation, what we do, we just have a basic overview how the circuit will behave in the...
I also don't, that's why I don't build this. I mean, if you really want to do that much, build hardware. You just like simulation, how much can you do? Simulation is to verify your control, verify the limits of what it is that's happening. But simulation, in my opinion, is efficiency and things like that have to be defined in the circuit, because it all depends on how you define your heatsink. Your switch may be anything, but you have to design your heatsink. You have to design the cooling. You have to design all these things.
At least for a switch, can we do, because we have to derate the switch according to the current, and we have to design the heatsink for that purpose. So for that analysis, maybe we have to pay attention for at least for the switch part. So is it possible for at least how to take the loss, calculate the losses which are incorporated in the switch? So as you said, we can put a series resistance of the typical value from the data sheet. Okay, and if possible, we can from data science, we can create a what we can say dictionary, and we can plot approximate plot of for what current and for what temperature what is the resistance, so that it can become more realistic, and we can plot the losses.
Okay, we can do that. That's always possible.
Okay. Thank you.
Okay, sure then. Thank you. See you next week. Bye-bye.